In this lecture, we're going to review molecular forces. We're going to look at the difference between intramolecular forces, which are actually bonds, and the difference between those and intermolecular forces, such as the three intermolecular forces listed right here. The importance of intermolecular forces is that they determine how a substance absorbs heat, how much heat it can absorb, and how it retains that heat. Intramolecular forces are bonds. Intra, as you can see here, the root intra basically means inside. So intravenous drugs are drugs that would be administered inside of a vein, or if you need to go get an IV from the hospital, that's an intravenous drip. It's something that goes inside your vein. Intramural sports are sports you might play in college that are just within, like scrimmage games that are between two different teams that are part of the same school. So it is inside of the school. So an intramolecular force is a force that holds atoms together within a molecule. So you have already learned about intramolecular forces, for example, the one holding the hydrogen to the oxygen. And in this molecule water, the intramolecular force that we see is a covalent bond. So this is just a quick review. We're going to focus this lecture on the next type of force, which is the intermolecular force. An intermolecular force is the force that is between. We often use a lot of words. We think of inter as being inside, but inter actually means in between. So for example, an international highway or an international flight means a flight between nations. An interstate highway is a highway that goes in between the two states. So an intermolecular force is a force between molecules. I'm generally going to refer to these as IM forces from the rest of this lecture, but know what that means is intermolecular forces. So there are three types of intermolecular forces which we're going to discuss. And before we go into much detail, I want to sort of do a review of why this is important. To look at the importance of IM forces, we're going to look at this animation from Pearson Prentice Hall. Intermolecular forces determine many properties of many different substances. For example, ice. Ice is a form of water, as you guys all know, but what is interesting is that many solids do not float. Ice, however, is less dense, meaning the solid form of water is less dense than the liquid form of water, which is very unusual for a substance. So let's look at why this occurs. If we were to look up water up close, here's the structure of water in ice. So in the solid form, we see all of these water molecules are in this is a crystal lattice formation. And what's highlighted in yellow is the hydrogen bonds or the intermolecular force that is occurring between these water molecules. These hydrogen bonds are going to be what causes this water molecule when it is in the solid state to make that crystal lattice structure. As the ice absorbs energy, you can see that the hydrogen bonds are weakened and now they've collapsed. And this is why the water is now more dense as a liquid than it was as a solid, because these molecules are now able to get close to each other. So as a substance, you can look at how much energy it can absorb before it is either going to phase change, or for example, if it's going to, how much energy it can release when it phases change. And that's all based on the types of forces that exist between the molecules. Let's first examine a dipole-dipole attraction. A dipole-dipole attraction is an attraction between two polar molecules. As you see here, we have two molecules of sulfur dioxide. Based on our previous knowledge of electronegativity, we can see that sulfur is going to be the less electronegative of the two different atoms within this first molecule, or both molecules. So sulfur is going to be less attractive to the electrons that are being shared between sulfur and oxygen, and sulfur is going to be left with a partially positive charge, while the electrons that are bonding these two are going to be more attracted to the oxygen, leaving the oxygen with a partially negative charge. The same thing is occurring with this second sulfur dioxide molecule, and what then happens is, just like all positives and negatives, we see an attraction. So opposites attract, and that attraction between these two molecules is an intermolecular force. It's called a dipole-dipole attraction because the positive side of one dipole arrow, you could think of this as a dipole arrow, is attracted to the negative side of the dipole of the neighboring molecule. Now, if you have a molecule and it involves hydrogen, this is a specific type of dipole-dipole interaction, which is referred to as a hydrogen bond. A hydrogen bond is not a true bond. It is not the same as a covalent bond or an ionic bond because electrons are not being shared or electrons are not being transferred. They're just being, they're already being shared, but they're not being shared between the molecules. There's no involvement or exchange of electrons between the water molecule on the left and the water on the right. But this is the exact same process where we have two polar molecules and the two dipoles are attracted to each other. Let's look at this in a little bit more detail. We can get a better understanding of dipole-dipole attractions and hydrogen bonds by looking at this animation put together by Northland Community College. So as you know, a water molecule is going to be a polar molecule where the oxygen is more electronegative, hydrogen is less electronegative, and so we see that there is a positive charge end and a negative charge end. When you have two water molecules, as we saw in the picture in the slideshow, there's going to be an attraction between the positive side of one molecule and the negative side of the other. Now in a sample, there's going to be a million water molecules, and so they are all going to form a big matrix of attraction. Now this lattice is looking similar to the one we saw in the previous animation, where it shows why ice is less dense than the solid. The Prentice Hall animation gives us a little bit more detail about why the polarity exists in this water molecule. So if we were to look at this molecule up close, and we look at the electrons being shared in the bond between hydrogen and oxygen in each case, we see that as oxygen is more electronegative, we know that it's going to attract those shared electrons more closely. Therefore, the oxygen is going to have that partial negative charge and the hydrogen is going to have the partial positive charge. The third type of IM force is one that occurs between non-polar molecules. This is called a London dispersion force, also called a van der Waals force. This force is basically just caused by a very momentary unequal distribution of electrons within a non-polar molecule. So we have an electron here and an electron here being shared by this H2 molecule. If these electrons are constantly going back and forth and being shared between the two, and if for a moment they are focused more on the left of the hydrogens, and at the same time these two electrons being shared by the second hydrogen molecule, if the electrons are being shared and they happen to spend a little more time with the molecule on the left, what we're going to see then is we're going to see this molecule on the left has a partially negative pole and a partially positive pole. The molecule on the right also has a partial negative pole and a partial positive pole. If this simultaneously happens, then we're going to have a very slight attraction between positives and negatives, just like you would in a dipole-dipole interaction. So this is a very weak, it is a very short-lived attraction, and it only occurs between non-molecules which are just happening to have an unequal distribution of electrons. In a previous video, we had seen this animation of a microscopic view of an ice cube being melted. What we want to focus on again is, now that we're familiar with different types of intermolecular forces, we want to look at these hydrogen bonds. And what we want to notice is that as these molecules are gaining kinetic energy, those hydrogen bonds have just disappeared and allowed the substance to go from a solid into a liquid. And we looked at this because this is the idea of heat was being absorbed and increasing the kinetic energy. So something to keep in mind about any type of intermolecular force is that as the molecules get farther from each other, which is usually occurring because they are gaining kinetic energy and gaining movement, then those molecules are going to have less intermolecular force. Let's look at the opposite case now. Let's remove kinetic energy and see how this substance will regain intermolecular forces. So now we see heat is exiting from our system, our melted water, and it is leaving and going into the surroundings. As these molecules slow down and become closer to each other, we see that the hydrogen bonds have reformed. So in the process of going from a liquid to a solid, as heat is giving off, the hydrogen bonds have reformed, and we can even look at, or we can even calculate, how much energy has been released or removed from this system by using some quantitative analysis with thermochemistry calculations. We'll focus on more on that on the next lecture.